All right, so I need to reorient myself to talk about natural language rather than breast cancer. Yes. So last week, what did we learn about? What we learned about last week was quite a bit of a fundamental issue in machine learning. In fact, some people does call it a fundamental problems in artificial neural networks. That is that can we actually do credit assignment using backpropagation procedure? This is a fundamental issue. When you build a large enough system, what needs to be done is that you need to look at the outcome of the system, compare it against the desired outcome, or you can even see how that outcome has been influential, either positively or negatively. Based on that, you should be able to assign the credit to each and every component along within the system. And then based on that, you know whether the system needs to be updated or whether the system needs to be modified or fixed or whatnot. And then if you recall the example that I gave about this kind of, let's say, offshore shell companies in order to avoid paying tax, that's exactly what they do to obscure the whole process. And then what is the way in which they follow in order to obscure this process of tracing back who has actually made any money or the proof for the money eventually is to make many layers of the shell companies whose ownership is very much opaque, and then thereby making it difficult for tax authorities to figure out how all those, let's say, credits or the revenues were propagated. So we talked about this fundamental issue, and then what we realize is it's just like in this kind of, let's say, tax avoidance scheme. The reason why the credit assignment is difficult with backpropagation is because we have multiple repeated layers of the nonlinear functions, right? And then whenever we computed the gradient or whenever we perform the backpropagation, we had to compute the Jacobian of this nonlinear layer that is often implemented as the linear transformation followed by a formalized nonlinearity. And then the Jacobian, unfortunately, had the term that multiplies the whatever has been backpropagated so far with the transpose of the weight matrix in this linear transformation. And then by doing it repeatedly, what we realized was that, unless we get super lucky so that the largest eigenvalue or the singular value of all those, or the matrix norm of all those matrices were exactly 1, is going to either blow up, the norm can blow up, or norm can shrink towards 0. And then we said that the blowing up is fine. Why is blowing up fine? Simply ignore, right? If credit assignment procedure tells us that everyone is to blame to the maximum extent, you say that perhaps backpropagation made some mistake. So we're going to just ignore that one for now. So that was fine, but on the other hand, when the gradient or the backpropagation error signal shrunk to 0, now that one was trouble. So why was there trouble? Because there were two potential causes that we couldn't really distinguish from each other. What were those two causes? What can cause this vanishing gradient issue?
Training just converged to local minima.
Right, learning is almost done. So we are indeed near the local minimum of this loss function, where the normal gradient will be almost naturally very, very small. What is the other possibility?
Like a saddle point or something.
Exactly. That is that if somehow we initialize the parameters in an incorrect way, so that the learning just never starts. So if you think about the non-convex loss function, if it's a strongly convex function, wherever you start from, you're going to go toward the minimum, because there's a single minimum at which the gradient is going to, norm of the gradient is 0. But in this kind of, let's say, highly complicated neural network, our loss function tends to be very complicated. And then we might actually end up starting from a place where the slope is simply 0. Then what would be such a case is that we initialize the weight parameters of, for instance, a recurrent neural net, such that the norm of the recurrent weight, U, from last week, was really, really small. Then already from the beginning, the vanishing gradient happens, and then we can't really move anymore. So there's no way to make progress. But the unfortunate thing, we can't really tell the difference between these two. Whether it is the incorrect configuration of the parameters or that the learning has ended, we can never. So that's the kind of, let's say, one interesting thing about machine learning or statistics is that the way in which we know how to solve a problem is via running this machine learning algorithm. What that means is that before running all these machine learning algorithms or the statistical analysis tools, we can't know what is there in the data. So the reason why I brought it up, bring this up is that because we are all kind of, let's say, trained in a school of engineering or science as to solve a problem ourselves. So here's a problem, we need to solve it. And we often think incorrectly almost always that we know how to solve it, or we know how it should be solved. And then often kind of, let's say, question what kind of solution this machine learning algorithm finds, or what kind of, let's say, statistics that have been computed. But then the thing is, if you knew that, you wouldn't use machine learning or statistics. So in order to tell what is in the data or how the problem should be solved, we have to rely on machine learning. And then this is one very representative example of that happens is that we can't tell whether a thing is going wrong or right because that is determined by the data. And then to tell whether things are going right or wrong, we have to look at the data. How do we look at the data? By training these neural networks. Training these neural networks is not only a way to solve a problem, but is also our way of looking at the data. Because at the end of the day, looking at the data and solving a problem are the same thing. So that was the issue. So how did we decide to address that issue? I know that you all know the answer because you've been asking all those questions on the campus wire. We decided to, let's then introduce all those shortcut connections via which the error can be backpropagated without having to go through every single intermediate layers, right? And one thing we realized is that if we introduce shortcut for every possible pair of layers, there are too many of them. That's going to make everything so much more complicated. So we will do so in a way that is we're going to simply copy over the previous layers activations, sum them to the next one. And it turned out that doing so introduces all those shortcut connections that we want, thereby allowing us to train a very, very big network. But then there was an issue, right? So when we have a finite number of layers, we can control the norm, so the growth of the norm of the forward activation. So the activations from the hidden layer, we can do that. But then in the case of the recurrent network, or in the application area of natural language processing, which is the whole point of this course, we often do not assume the bounded length. We want to build a system that is able to work with the text of any length. And when we do that, the issue is that we can't really control how many steps or how many layers this network is going to go through. Thereby, we can't really control the growth of the norm of the forward activation. So we're not talking about the exploding gradient, but we even have to worry about the exploding, let's say the forward exploding forward pass. So that's not that great. So what was the kind of, let's say, reasonable, let's say, solution to that was to introduce what we called an update gate that allows us for each dimension, right? For each dimension, compute the convex combination of the previous steps activation and the new candidate activation. So that's how we introduced the update gate. And we also talked about the reset gate, but reset gate is not really needed. That's not really needed. So it's okay. You don't have to know about them. And then that's true because I arbitrarily added that one myself in 2014, and then now that I think about it, I didn't have to do that. It just slowed down the whole experiment by some factor. So we learned how to do that, and then these are how we all end up with all these residual networks, highway networks, gated recurrent units, long short-term memory units, or whatnot and whatnot, whatever you can imagine. This is how it all started. So in the case of LSTM, because I heard that there are some of you had some questions about the idea. So how does this whole discussion connect to long short-term memory units? LSTM is essentially the same thing as well, except that how all those gates are implemented is a bit different. But at the end of the day, what happens? The most important thing that happens within long short-term memory unit is that if there is a hidden vector called cell, so C, the cell is updated by adding a new value to the old cell value. So we just add. And those introduce all those shortcut connections. And then there's input gate, output gate, forget gate. I'm pretty sure none of them is actually that necessary anyway. So the most important thing, shortcut connection, linear shortcut connection via which the error signal can be propagated back without having to go through these intermediate layers. Okay, so that's what we have learned so far last week. So any questions? Or is everyone perfectly clear on what we have learned?
What do you mean by they're not really needed? All we need is the shortcut.
All we need is shortcut connection. That's actually true. So these days, a lot of people started to just use the paper title to be as a joke statement. So they all say that all you need is X, but literally the shortcut connections are the most important thing when you try to build a very deep neural network or the neural net that works for a very, very long time.
These different architectures have learning improvements, right? Or also the
Not really. Not really. That's what everyone wants to say, but in reality, that's not really true.
So in practice, is it really possible to train bounded?
What sequence?
So theoretically, we can train bounded sequences.
Right.
Mm-hmm. In practice, is it really implementable?
Right. So can we actually train a recurrent net that is able to handle a truly unbounded, infinitely long sequence? The answer is yes. Answer is yes. Answer is yes. Now, of course, how we learn, how we train this model is to compute the gradient by the procedure of backpropagation or the backpropagation through time in the case of sequence, because we always think of sequence as a time series. What that means is that in order to compute the gradient of the loss function with respect to parameters, we have to read the entire sequence and then backpropagate the error signal all the way back. Now, unfortunately, if the sequence is infinitely long, we'll never arrive at the end, and we'll never be able to backpropagate the error signal all the way to the beginning. So in order to avoid that kind of issue, there are many different ways to tackle it. One is that we simply say that if we're going to just go up to, let's say, I don't know, 100 steps, backpropagate back, update the parameters, and then for the next 100, we do the same thing. So it's going to be more like a truncated, so-called truncated backpropagation procedure. Now, truncation can happen both in the backward and then both in the forward as well. Now, unfortunately, this one is pretty approximate. So another approach is to compute the gradient on the fly. So if you recall how we computed the backpropagation, what we did was to go forward and then try to come back, and then for each of the point at which at each of the point the layer was evaluated, we computed the derivative. That's what we did, and then we just trained the derivative. On the other hand, you can think of doing the other way around. So I'm going to go forward, and I'm going to say that this is the input, and then at this point, these are all possible derivatives I get, and then I can carry it over as I go forward. What that means is that in fact, you can compute the gradient without having to do the backpropagation. You can actually compute the gradient on the fly as we go forward. Then that's called forward modal auto differentiation. It really, again, comes out automatically from the basic calculus, except that it is computationally extremely heavy. But in reality, we can do some stochastic approximation there. Unfortunately, that's out of scope of this course. I don't think any of our courses teaches that, but all you need is to read one paper that was written by one of the PhD students at neuroscience department here at the JMR on the review of this online learning algorithm for recurrent neural network. It's a bit dense, but it's great. It's reasonably dense, All right. So any other questions before we continue with the moving on to the next topic?
Even with the shortcut connections, we still don't know whether it's a local minima or a saddle point, right?
Yeah. So we cannot tell whether we are in the local minima or in the saddle point, unless, of course, we can try to compute the higher order statistics to check that. But if you imagine how the higher order statistics look like, so if you want to compute the Hessian, what is the Hessian matrix size? It's the number of parameters by number of parameters. We're talking about the neural net that has millions, if not billions, of the parameters. So the Hessian can be pretty large, and it doesn't really help us computing them explicitly. So yes, we still cannot tell, but one thing we know is that if we have all these shortcut connections, right, linear shortcut connections, then however we set the recurrent weights, the vanishing gradient is not going to happen because of the ill-configured recurrent weights. So even if the recurrent weight is not configured well, we know that there will be some gradients via this shortcut connection. So that's the one thing we need. All right, but enough about the recurrent net, I guess, because who actually trains recurrent net these days, except for me and a few other people who work on RL and so on, right? So we are going to actually move on to what people actually mean by attention is all you need, right? So we're going to start with the gated recurrent unit that we introduced last week. So we say that the HT equals UT is going to be the update gate, element-wise multiplication, sigma of UH minus 1 plus WXT plus E plus 1 minus UT, element-wise multiplication, and H minus 1. Now let's try to unroll this recurrence equation. This is recurrence equation, right? Because I have the HT here and the HT minus 1 here, and as t goes up, I'm going to apply the same thing over and over. So in the very first one, H1 equals U1 times H hat 1. So I'm going to use the hat HT to indicate that this is a candidate hidden vector. So this is going to be H hat T. Plus 1 minus U1 times H0. And H0, as we talked about, we can just assume it to be 0, or it can be learned, but learning H0 is identical to in fact setting it to 0. And then now H2 is going to be U2 times H2 hat plus 1 minus U2 times U1 times H hat 1 plus 1 minus U2 square, U2 times 1 minus U1 times H0. The H3 is going to be U3 times H3 hat plus 1 minus U3 times U2 times H hat 2 plus 1 minus U3 times 1 minus U2 times U1 times H hat 1 plus 1 minus U3 times 1 minus U2 times 1 minus U1 times H0. And we can just go on and on and on until the capital T happens. But I can show you that how it looks like if I look at the just HT. HT is going to be sum of HT prime going from 1 to small t, UT prime, so gate at time step T prime, times, here comes a product. So this is going to be a product, the element-wise product. T double prime going from the T prime to T minus 1. 1 minus UT double prime times H hat T prime. So let's see where things comes from. So this one is essentially the one at the very outer portion. And then here we have we have the multiplication of the 1 minus 8 from the previous steps. And then these are these. Then you can write it like this, but that's it. It's not really important, right? So if you decided to use not the update gate, but 1 minus update gate, if you decided to use the input and forget gate, all pretty much the same thing. But the important thing here is that at any time step t, if I look at the hidden activation of a recurrent network in this kind of gated recurrent network, it's going to be written down as sum. So weighted sum of the candidate hidden vectors at all the previous time steps. That's the most important thing. So the hidden activation at the tth layer is going to be the weighted sum of the candidate activations from all the previous layers. And then this happens because of the linear shortcut connections we have created, right? So because of the shortcut, it turned out that whatever we computed at any layer t is simply sum of what we computed in the all layers. And then because we introduced the update gate instead of the just using identity, we get some kind of weighted sum. So very important, this notion that it's a weighted sum. So let's rewrite this in a way that makes it a bit easier to write. So we're going to go through the same steps. Then we say that, okay, here's going to be some weight that is WT prime. I don't know why I'm just going for the superscript over and over, but WT prime, XT prime, H T prime minus 1 times H T prime hat X T prime and H T prime minus 1. So here's the first one, here's the second one. Now where does the second term comes from? Second term comes from here. H hat T is a function of HT minus 1 and XT. So whatever the input we got, then what was used in the previous time step. So that's what we get. And then this weight, which is a product of all those update gates. And then if you recall how we computed the update gate, this weight can be thought of as a function of the previous time step hidden state and XT prime. So this is really, we're not adding and introducing any further information, but this is just another way to view it. And then making it much more explicit that the hidden state we compute at time step t or the layer t is the weighted sum of the hidden state, candidate hidden state we computed at all those previous layers. Although one thing I want to point out here is that although it looks like it's just a linear sum or the linear term with respect to h hat t prime, but that's not the case, right? Why is that? Because there's still the recurrence. So ht is a function of ht prime minus 1 and all the previous ones, and then you notice that all those previous steps activations are the function of the previous one. So it looks like it's just a weighted sum of some constants, but that's not the case. It's very much recurrence. It's just a rewrite to make it clear.
The W here?
Sorry?
T prime.
WT prime, yes. WT prime is this. So we're just using WT prime to indicate how we compute this weight.
So in this notation, like you're saying it's a function of x t prime and h t prime minus 1, but
Yep.
is that like, are you concatenating those together, or you just kind of?
I mean, it can be some you can write, so you can write this as the function of this. That's just what it
Okay.
is. Is that the idea how it's implemented is this probably something complicated. But it's something complicated. But I don't really care about it at this point. I just want to very make it explicit that the HT is the weighted sum of the H hat T prime, where T prime goes from 1 all the way to T. That's the most important. So then what we're going to do is we're going to break this recurrence. Recurrence over the temporal dependency. Before we do that, we need to think about it. Why do we want to do that? Because if this was not recursive, then we can just compute the whole thing all together, sum them, and then get the HT. So we're trying to see if we can actually make a more efficient version out of it by breaking this kind of temporal dependencies. So the first question I want to ask along this line is that what if each candidate state, so that is that the H prime hat was computed independently. So that is, if you look here, this H hat T prime is a function of H hat T prime minus 1 via H T prime minus 1, right? Because H T prime minus 1 is going to be a function of the hat H T prime. There is that recurrence relationship. What if we just compute all of them independently? That is, we're going to change it so that HT is going to be computed as a sum T prime equals 1 to T W T prime X T prime H T prime minus 1 times H hat X T prime and T prime. So instead of having this H hat be a function of the H T prime minus 1, we're going to compute H hat as a function of X T prime. So the input at time step T prime and the time step itself. So here's the input. So something like, in the examples that we talked about, the lion is chasing a deer. What we're saying is that for each location, we know the location that is time step T prime, and then which word appears in that location. Now, given that information alone, let's try to compute this candidate hidden state H hat. Then we'll do that for every location, all simultaneously. So this can be computed across H prime 1 all the way to, in fact, the capital T, right? The entire thing in parallel and computed in parallel. And then why do we actually add this T prime is because we wanted to ensure we have some kind of positional information. Because we did talk about it at the very early stage of this course, is that the words often have the meaning that is roughly translation invariant. Cat at the very beginning of the sentence is still the cat at the end of the sentence. However, that's not always true. That is not always true. Sometimes some words, depending on where it appears, even without knowing the context, the meaning may very well change. So the fact that the words are appearing in the second location, so think about a word fly. Fly can be an insect fly, or the fly can be a bird fly. So taking off the tongue, right? And then if the word fly appears in the second location, or the, let's say, third location, very much likely that it's going to be a verb, or with a small chance that it's going to be an insect. However, if the fly appears out on some random location, like the seventh location or whatnot, probably a higher chance of this being an insect. So we want to preserve a bit of a positional information. Now, in this original scheme, where does the positional information come from? The positional information actually comes implicitly via the fact that in order to compute the H hat T prime, we actually have to compute all those previous hidden states. And then that allows this H hat T prime function to maintain the position if it needs to. But we want to keep it. So this is often what we call positional embedding. So you can imagine that you can also embed positions into a vector space, just like what we did with the words. Position 1 is going to have some vector, position 2 is going to have some vector, position 3 is going to have some vector. Now, the reason, because we know that the locations have a very clear meaning and the similarity, right? 1 and 2 are closer to each other than 1 and 100. In that case, we can actually encode a bit of a, let's say, this knowledge by saying that perhaps the positional embedding should change in a way so that the embeddings of the nearby locations are closer to each other. Very easy to do it if you want it, but in our often cases, you don't really need to do that. So just go use a PyTorch or the Hugging Face as a positional embedding is going to do it, everything for you. So this is the first one. Now we can compute H hat T prime, that is the candidate hidden states, all in parallel, independently of each other. So what is the second thing that we can ask? Second question we ask is, what if each wave, so WT prime, was computed independently? That is, HT is going to be now sum, the same sum is always same. And then W of XT prime, XT, and then T prime, and then T times H hat XT prime and T prime. Now this is what we are looking at here. Now let's see. What was this weight WT prime of the XT prime and HT prime minus 1? What did it say was that for current time t, right? For current time t, I'm trying to assign a weight to each and every previous location. That's what this weight is. It looks at the hidden state and the input that was used to compute the new hidden state at time step t prime, and then we try to assign the weight importance to the particular time step, given that we are currently at time step t. Right? So we're at time step t, and we're trying to look at every single previous time steps, the t prime going from 1 to t. For each one of them, we are assigning weight. So then, if we wanted to compute those weights all in parallel, what are the information that we need to do? We need to give the information that what was the input at time step t prime, what was the location of the t prime, and then what was the input what is the input at current time step t. So it is looking at what is the input at current time step t, and then the location t itself, and then tries to compare against what was given as the input at time step t prime and what the location of the t prime is. Now this is not still as powerful as the original weight. Why is that? In the case of the original weight, by the virtue of having access to ht prime minus 1, in fact, the weight was computed not only using the input at time step t prime, but using all the words up until t prime. Now here we are saying that if we have to do that, we can't really compute everything in parallel. So instead, we're going to do so by looking only at a particular word that was given at time step t prime and the positional embedding that corresponds to t prime, and then what has been given at the current time step t. Then now we can compute this weight for all the previous locations simultaneously in parallel without having to wait for some of them to be computed before some others can be computed. Right.
So to kind of summarize, the benefit of the first one is that it's better at preserving past information and the relationships between it. And then the second one is potentially more efficient because it's doing everything in parallel.
Right. So this one is awesome because we're looking really at all the previous context so far. This one is awesome because we can now compute all these things in parallel. Now, strictly saying, computational complexity-wise, they are roughly equivalent with respect to the length because of the summation. In order to sum them, we can't really do much other than actually sum them, right? If you want to do the exact sum. Now, obviously, we are now in the era of the randomized algorithms and so on. So sometimes we can actually do the summation in a sublinear time with the sum tolerance on the error. But generally, we need a linear time. However, the fact that we started to use all those modern computing devices such as GPUs that support a heavy let's say, parallelization of a simple compute unit, often the latter, these approaches can be substantially faster. So the reduction by sum can be so much faster than doing the matrix multiplication over and over for the same length sequence. So yes, so answer is no and yes. So it is computationally not much more efficient, but in reality it's extremely efficient. Yes.
So the second method is still look at the entire context, right, up to point to time t. It's just that it doesn't look at each compressed representation like step after step.
Right. Yeah. So this is really good point. Is that for computing each and every one of these weights and candidate hidden state, we only look at that particular position, the input at the particular position. However, by solving all of them, the HT, this vector itself, is computed using the entire sequence of the previous one. It is highly contextual, except that how we compute it in individual terms before summation is extremely parallelized. So far, so good? Yes. So then now let's try to see how we can implement each of these components. So first, let's look at the weight. How are we going to implement weight? Well, we're going to, so implementation. So the weight is going to be implemented, so W of xt prime, xt, t prime, and t. Okay, so this is here. We will implement this as the softmax actual function. So we have the x here, then q of xt at t. So this is the input at xt, and then time step t, transpose k of xt prime and t prime over the sum that goes from t prime equals 1 all the way to t, except of q of xt and t transpose k of xt prime and t. And how we're going to refer to this q and k as a query and t. So let's see what this does. So we are comparing xt prime at the location t prime, and then xt and location at t. Now you can imagine that for each and every previous time steps, let's say what we have received so far, as the rows in a table. So we have a database, and then each row corresponds to the input at each time step that is before t. And then what we do is we are trying to query the most relevant rows from this table, and then the query is given by what the input is at time step t. So that's why we are going to compute the query vector out of xt and its location t. So this will be some kind of query vector, so d-dimensional vector. And then this query is going to be compared to, if you recall from the database course that you may have taken if you're a computer scientist, then we're going to compare that to the key of each of the rows, right? So key column, so we're going to use a key column that is used to index the rows in a large database system or the table. And then how do we compare them? One thing that we have been very, very consistent throughout this course so far is that whenever we are given vectors, we often use dot product, almost always use dot product to tell how well aligned, how compatible those two are. So we have a query vector, then we have a p vector, we look at the dot product to see whether the particular row in this table that corresponds to t prime row is compatible with this query that is based on xt. So that's going to be the score. And then we use the softmax function to normalize them so that if we get the weight assigned to each and every row so far up to t prime, so that the weights are non-negative or actually positive, and then they sum to 1. So this is how we're going to implement the weight. So weight, and then this uses all the information. It uses the content of the time step t, and then the location itself of the time step t, and then content at every previous step, and also corresponding locations. And let's see. And now, once the weight is done, what do we need? We need to think about this candidate state. So H hat xt prime and t prime is going to be computed as some function v that takes as the input xt prime plus p of t prime. Now, what do they look like? You kind of, let's say, can guess at some point. This P of T, you can think of this as, but this is the positioning that, just like if we use the E of W earlier, in order to indicate that there is the word embedding of the input W, P of T prime is going to be a vector embedding of the position T prime. Now, how would you implement it? You can implement it as table lookup, you can implement it as all those crazy sinusoidal functions or whatnot, but the actual embeddings themselves are not that important, as long as those embeddings are able to capture the similarities among all those locations. Now then you might ask, why don't we just use the actual numbers? Because they have the perfect similarities among the locations. Turned out that that's not necessarily true, because things actually oscillate, right? There are cycles, so some positions are actually closer to each other than some other positions, even though they are right next to each other, both of them. So we often want to learn this positional embedding. So that's a positional embedding. And then this V is value. So now you can imagine this as we try to query a relevant row by comparing the query against the key, and then we get the weight, and then that weight is going to be used to choose the value associated with that row in the table. Now let's imagine that the magnitude of this query value vector as well as the key vectors are taken to infinity. So we're going to look at the angles, but then we're going to say that the magnitude is infinitely large. Then what happens is that this softmax operation is going to return the one-hot vector. Whichever aligns best according to the angle is going to have the value 1 as a weight and all the other zeros. That's effectively selecting just one element. And then what happens to that selected element? That element's value, so that row's value is going to be returned as the hidden state at time step t. And then how do we compute the value? The value is going to be a function. So this, you can imagine this as some kind of linear transformations or any kind of neural net that you implement that takes as input the content at time step t prime, the input at time step t prime, plus the positional embedding. Can be concatenation as well, but as you can imagine, as we go into a higher and higher dimension, concatenation, summation, they all start looking pretty much same. Because you can't really tell the difference between the, I don't know, like the million dimensional versus, let's say, 2 million dimension, or the summation of the 1 million dimension, 2 or 1 million dimensional. But you see what I'm getting at, right? So we're going to implement it like this. And then again, it looks like almost everything can be computed in parallel because this dot product can be computed in parallel. Exponential function can be applied in parallel. But it's not truly parallel because we have this normalization term that cannot be computed in parallel. But again, reduction, so summation by reduction in these modern compute architectures, extremely efficient, can be done like very easily. And the value can be computed all independently. So things are actually really efficient if you implement it like this. And still at the end of the day, it uses exactly the same amount of information that was provided. What was it? Was the actual sequence. Up to time step t. So far, so good, yes?
Are the key and value functions related at all, since they both relate to the content of the?
Yeah, so you can imagine the query and key and value. So let's think about the key here, key and value. So what you imagine is that you are going to build, let's say, database of all the students at NYU, for instance. And then you want to provide a very efficient search over all those students by their name. What would be the way for, what kind of, let's say, key would you use? you might probably want to start by using, oh, the primary key is going to be last name. The secondary key is going to be first name, just because our implementation, our interface is going to ask user to start from the last name, search for the students and so on. So you can imagine that this key is extracting a part that is relevant, or we're actually finding which of the content is relevant for the particular query vector. Now value is, now once it's extracted, what are the actual information that we want to return? So they are obviously related because they all use the similar input, not necessarily same, similar input, but yes, they are related, but they just extract they just expose a different aspects of the input. But again, they might actually converge to either exactly same thing, and then it is perfectly fine to use the identity function for QK as well as P. That's what we did in 2014 initially. Okay, yes.
But for the expression of W at the denominator, should it be like a T prime memory loss, like K X T prime K prime? The denominator at the end.
So,
Like in the denominator at the end of that expression, like should it be
oh
like
yeah, T prime, yes, you're right. T prime, here, yes, okay. Now, it turned out this is sometimes just not enough, because there are many different ways to tell what kind of neural net is going to be powerful or not. There are many ways to do so. One particular way to do that is to think about how many layers of computation is being done. And then that actually connects to the computational complexity theory, as well as the circuit complexity. Is that for instance, if you think about it, let's say if I wanted to sum two binary strings, can I actually do the summation in the time that is shorter than the number of bits in those in one of the strings? Impossible, right? Now, if I wanted to do the multiplication of two binary strings, then what do we need? Clearly more time than just scanning through one sequence. So the time complexity is not going to be, and then we know exactly what are the kind of, let's say, time that needs to, or the amount of computation that needs to be done, at least in order to solve a certain set of problems. So what that means is that we can now look at how many layers of the computation is being done in order to roughly guess which of these two neural nets can compute something more complicated than the others. And if you look here in the recurrence case, the number of layers, right? Number of layers, and whenever I say number of layers or the layers of computation, it's all nonlinear. Cannot be linear. If it's linear, it's as if we didn't do anything. So the number of the nonlinear layers when we compute the HT is in the order of T. So we go through the at least T many nonlinear layers of computation in order to arrive at T. Now, on the other hand, if you look at this one, then what you see is that the number of the nonlinear computation that is chained, right? It's the layers, right? Layers is maximum number of the nonlinear layers of computation to get to HT is actually only 2, right? Computing the value, right? That can be nonlinear if you wanted to make it. Computing, let's actually scroll down a bit. It is computing a value and then summing them. So it's actually 1. Okay, so positional embedding, so 2, that's it, right? So what that means is that there are a number of things that this version cannot do that the recurrent version can do very well. Recurrent version can count very, very easily. It can memorize, it can also compare different locations much more easily. In this case, you cannot make all those comparisons. So here, can we actually build, so let's think about this. Okay, if I have a sequence that is unsorted, now I want to find the maximum value in this sequence. How many operations do I need? In the worst case, the length of the sequence. In the best case, still the length of the sequence because we got to compare, right? You can't do that with this. you cannot, because you cannot really compare all those numbers, right? You need the n many comparisons because you pick the best one, or you pick the whatever is largest so far, and then you compare to the next one. If one of them is larger, you keep that one, and then you continue. You cannot do the comparison, n many comparisons, so you can't do that. So what that means is that generally, we have traded off computational efficiency. Well, okay, hold on. Traded off the computational power for the greatly increased computational efficiency. So we want to somehow, let's say, overcome that issue, that trade-off. So one way to do so is to introduce multiple attention heads, where the attention corresponds to this whole procedure. So what do we mean by having a multiple heads is that at each time step t, we will have HTM, where M refers to one of the multiple attention heads that we're going to have. Then that one is going to be sum t prime from 1 to t, weight of that particular attention head as a function of x t prime and xt. I'm going to omit the t prime and t because they are always coming together. We're just at the positional embedding times h hat m x t prime and xt. Oh no, t prime. T prime. I'm just omitting the positional information. And then what we do is that our ht is going to be the concatenation of ht1, ht2, htn. So and then for each of these head, we're going to have a separate query key and value, as well as even the positional embedding, if you want, functions. So we're just having the okay, here's a new time step. We're going to just do this procedure of attention multiple times using different ways. And then what does that tell? What can it do is that it can actually tries to look for different relevant pieces from a different aspect. And then you can do it for n many times. So it actually helps getting more information. I do have some reservation on why whether it's actually needed. Because at the end of the day, I think that just stacking them up should be much more efficient. But well, this makes sense, right? And then one thing that is really, really important here is that this procedure, we're going to assume for now that this value function is just a linear transformation of the input xt prime. I'll just assume that one for now. It doesn't have to, but for the purpose of the discussion as well as the practical, let's say, use, the value function is often a linear function of the input. And then what that means is that however many attention heads we're going to have, the resulting hidden state at time step t is going to be a linear function of the actual input. Right? Because it's just weighted sum. And then this h head is going to be just a value function that is a linear function of the input. So what that means is that the attention on its own is very much just linear. And then what's the one thing that we learned is that if you have linear layers, that's having many of them doesn't make any sense. What we really need is some kind of nonlinearity. So what we need is that we need to know. This is a term that I just made it up, so you don't have you won't find it anywhere. But we really need some kind of nonlinear fusion of all these outcomes from the multiple attention heads. In other words, instead of doing so, we do ht equals some nonlinear function like the neural network that takes as input the concatenation of all these attention heads at time step t, and then this has to be nonlinear. So we're going to fuse the information in a nonlinear way. And then by doing so, we achieve two different things. One is that we can change the dimensionality of the output from this multiple attention heads so that there is not going to be the function of the number of the attention heads. And the second purpose is to actually improve make the computation non-trivial, because the linear computations are often very, very trivial. But then you notice that if you do that, we're going to add a nonlinear layer, so we're going to suffer, we can potentially suffer from vanishing or the exploding gradient. So in practice, how the implementation is often done as with the residual connection. So this H tilde corresponds to this concatenated version, going to be max of 0 UF times max of 0 WF H tilde T plus BF plus CF plus XT. So this XT is the residual connection. This is the one nonlinear hidden layer, two rectified linear unit layers that we add. Then by doing this, we introduce the nonlinearity, but also because we're going to introduce the short connection, the training is reasonably okay. This is a very difficult condition problem. Okay, so far so good, and this is what the modern day attention is. And here at this point, looking at this, what you notice is that there is no temporal dependency. Right? There is no temporal dependency. And what that means is that to compute HTM, is it really true that we only have to run this summation from 1 to t? Can we, in fact, compute or run this summation across the entire sequence? Looking at the future as well. And it turned out to be possible because there is no order in which the sequence needs to be processed here. So it's almost like at this point, what we have is not a sequence, but a set of words or the tokens that are tagged with their locations. And that's how you end up with the so-called self-attention. Or some people like to call it non-causal attention, where the causal, like this word causal comes from signal processing rather than the actual causal inference literature. Then here, only thing that we're going to change is that the HTM is going to now be a weighted sum as usual. So WM, XT prime, XT, T prime, T times H hat M, XT prime and T prime. But the summation goes from T prime 1 all the way to capital T. So by doing this, at every time step, we're going to look at the entire input sequence and then try to compute the new hidden activation. Now, this is very different from recurrent network earlier. When we use a recurrent network, because of the nature of this recurrent, let's say, sequential processing, we can't really compute the hidden activation and time step T using the future words that have not been processed. Of course, in order to avoid or to address that issue, what people have done so far is, back then had done so far back then was to run the recurrent network twice. Once going forward, the other time going backward. And then we concatenated the vectors from the forward and reverse recurrent neural network. But in the case of self-attention, that's actually not necessary. We're going to compute everything in parallel without regarding whether the indices of these inputs are from the future or not. Then this is what people started to call self-attention. And then by stacking this self-attention layer. So what are the things that are needed to build this self-attention? We have attention heads that makes everything parallel, computation parallel except for the summation part. And then we have this nonlinear fusion So we need to have this kind of nonlinear fusion with the residual connection. And we are not going to be causal about how the vector is produced, but we're going to look at the entire sequence. So making it into self-attention. Now putting all of them together, what you get is so-called a transformer. So you stack all this layer that consists of the multiple paths of attention, and then the nonlinear fusion that has the residual connection. And then this attention is going to look at the entire thing. The layer, you stack it one at a time, and then that's how you end up with the transformer from Ashish Vaswani in 2017. And that's one of the state-of-the-art approach to solving a sequence modeling. And then you, of course, now here you have to be one thing careful. You use the self-attention that is non-causal attention only when you can. Now, what does that mean? If you're going to use this self-attention or attention in order to solve the problem of language modeling, then you still cannot use the input from the future, because what is the goal of autoregressive language model? Is to train the next word prediction. If I see what the next word is, that's not next word prediction anymore. So in that kind of scenario, you have to still be careful and then use causal attention rather than non-causal attention. But the only thing that changes is whether you're going to sum all the way to the time step t, capital T, or just small t. And in practice, implementation-wise, you're going to use a clever, let's say, masking to mask out the future, let's say, vectors when you do the summation. So still all things can be done in parallel during training. Now, if you want to sample from this autoregressive model, of course, you have to compute the first conditional, sample, feed it back in, compute the next conditional, sample, feed it back in, and then so on and on. So you have to do that. Now, although we did talk a lot about the efficiency of this whole thing, but is it really more efficient? So it is efficient in a sense that you can compute everything in parallel. But if you notice it, for every time step t, we have to run this summation up to t, or even to the capital T. What that means is that if you look at the processing the entire sequence, the computational complexity is in fact quadratic with respect to the length of the sequence. Now, in the case of the recurrent network, it was actually the sequential processing, so it was linear. So if you think about the computational complexity with respect to length, in fact, the attention is significantly more expensive. But during training, because we can always just compute all those things in parallel, it's often quite efficient. So that's how we actually derive the attention mechanism from first principle. In fact, we studied everything from the linear text classifier in the first week, or actually from the second week. So this is the kind of, at the moment, the most important building block of building a natural language processing systems. And then how we get here is just following the first principles we can get here. So then this largely concludes what we are going to learn about in terms of parametrization, right? So if you recall why we started talking about recurrent network, it was because recurrent net was deemed one good alternative way to parameterize neural net that is able to work with the variable length sequence without any kind of bounding. And then from there, we wanted to make it more efficient for the modern infrastructure that allows us to perform a heavily parallelized computation. We started moving some of the steps, adding some of the steps, and eventually we got into this attention. Then this is going to be essentially the end of our discussion on the parameterization, because this one really has everything that is important, right? What is it? It has a shortcut connection. And it actually has a shortcut connection across all those time steps. That's how we got the GRUs. And then it has the nonlinear computation, which we know we actually learned ourselves with the example that is really, really important. And then you can actually work with a variable length sequence. The length doesn't really matter. So this is essentially kind of, let's say, almost the end stage of the modern deep learning when it comes to parameterization. So this is going to be that, and then from here on, we're going to talk more about, with this kind of amazing parameterization, techniques that we have, what kind of problems can we solve, and then what are the other things that we can do beyond the overall regressive language model. We're going to take 5 minutes break, and then so we'll come back at 6:12 and then continue with the so-called masked language. Yeah, it's just a scalar. You can think of this is a scalar. No. So I didn't say this.
You gotta go.
It's a different. Yeah, and then this is what no, because
Okay, yeah, I get it.
If we are- So that means you cannot solve it. It's not solved. We can't gradually All right, okay, let's come back. All right, okay. All right, so let me just quickly see, so we have 20 participants all over the Zoom. How many do we have here, you think? How many? How many? I don't know, roughly about 30 or so. So how many do we have in the first row? Let's see, 7, probably let's say 8 personal row. Let's see. Okay, yeah. So about 50 or so. It's okay, you can sneeze. As long as you don't feel sick, I mean, the people sneeze for various reasons. All right, sounds good. So in fact, the participation rate is actually pretty high. Okay, so we talked about the attention. Now we're going to come back to another kind of aspect of learning, that is the post function, and then what is the distribution that we talk about. But before that, let's talk about one thing, that is that what kind of problems we solve in natural language processing. We often think about natural language processing. We immediately come with, let's say, question answer. So given a picture, let's say, question, we want to answer. Maybe some kind of common sense reasoning is also considered natural language processing, or perhaps some kind of relation extraction. Now, given the text and a given two entities within the text, what is the relationship between those two? Perhaps machine translation could be considered as a representative machine in natural language processing. But one thing you notice by talking about this is that almost everything in natural language processing can be thought of as so-called in-painting problem. Now, what is in-painting problem? As soon as you hear the word in-painting, whatever comes to your mind is precisely that, is that when you have an image and then some parts are missing somehow, and then you want to fill it up with respect to the context, that's in-painting. Now, in the case of the text, what is the in-painting there? You're given a text, you're going to remove some parts, and then you're trying to fill it up with the correct, let's say, missing portion given the context. And it turned out almost every problem that we run into in natural language processing are in-painting problems. And it's almost inevitable that this has happened because natural language processing or the natural language or the human languages are precisely the means by which we convey meaning to other people. We exchange ideas in natural language. What that means is that whatever we do with the natural language has to be in the form of natural language. So for instance, relation extraction. Let's say I gave you the Wikipedia page of the President of the United States, and then I'm going to ask you that, okay, the two entities are Barack Obama and the United States. Now, what is the relationship between them? It is equivalent to saying Barack Obama, and then missing portion, the United States. Now tell me what the missing portion is. Then the missing portion is going to be was the 44th president of. So there is a relation extraction. Now in the case of the common sense reasoning, let's say there is some kind of scene that is happening, and then I'm going to describe to you what the scene is. Jane performs an emergency surgery on John because John was in a, and then the common sense reasoning tells us that the John must have had some kind of accident. So for instance, in a car accident. But this one, if you think about it, is actually just an in-painting. So we gave you the textual description that is incomplete. The incomplete part is the part that we had to use our common sense to reason and then fill in. question answering too obvious, right? If the question was what is Wikipedia, essentially that is trying to inpaint Wikipedia is, and then the rest of the sentence. Machine translation, same thing. Essentially, I'm going to say something, let's say in Korean, 뉴욕대학교는 뉴욕시에 위치한 사립대학교이다. And then you're going to say, Professor Cho, what was that in English? And I'm going to say, oh, 뉴욕대학교는 뉴욕시에 위치한 사립대학교이다 is in English. I'm going to inpaint it, and then that's going to be the translation of it. So this is really an interesting thing about the natural language processing as opposed to many of the other problems. So if you think about the computer vision, let's say object recognition problem, images are given, but then what we're trying to do, what our goal is to classify those images into these concept categories, right? And then those concepts are not actually given as images. Concepts are in fact given as natural language almost always. And if you think about the, let's say another problem, what would be another problem? Because I told you about the talk that I just gave right before this lecture, breast cancer screening. The mammogram or the X-ray of a patient's breast is given, but whether the patient has a cancer or needs to be recorded for the follow-up, let's say imaging or the exams, is not given as the X-ray image of the patient's breast. It is given as a concept, and the concept is almost always explained by natural language. On the other hand, with the natural language processing, problem description, problem instances, question, the input, output, all of them are almost always given in natural language form. And then this actually gives us a lot of, let's say, interesting things we can do. And then you may have already heard about the so-called GPT-3 from OpenAI, and then you have the various other large-scale pre-trained language models, and then how those language models can be used to solve so-called, and then very incorrectly termed, I gotta say, so-called zero-shot learning problems, where we are going to just ask the language model to answer some questions for us. Who is Barack Obama? And then language model is going to tell us that Barack Obama was the 44th president of the United States. And then we're going to ask the GPT-3 that what is the translation of the New York Daejeon and New York Daejeon? It's going to tell us what that is in English. And then as you know, it already works, and then we can generalize it so that we don't have to work with the autoregressive left to right paradigm, but we can think about training a model that's going to really solve the problem in painting in an arbitrary manner. Doesn't have to be always that the question comes at the beginning and then we ask the language model to, or the NLP system is going to fill up and paint the rest. It can be anywhere. So that said, let's think about what inpainting is. Inpainting, the problem of inpainting can be thought of as argmax of y, argmax of the log p of x. I'm going to write it as pre y x post. And then x pre is a sequence. And then x post is also a sequence. So this is, you can think of this as a prefix, and in this case a suffix. And then y is also a sequence, but this is what is missing. Then we're trying to figure out, given some prefix and some suffix, now what should be the middle portion that is missing? Now in the previous example of Barack Obama was, that's going to be x pre of the United States is going to be x post, and the y is going to be whatever is in the middle, and then there is a relationship between those two. And then if we can solve this, that's awesome. And what you notice is that this is just a concatenation of the prefix, missing portion, and suffix. What that means is that the language model can solve this. With the language model, we can solve this problem pretty trivially. Because what does the language model do? It scores how probable a given sentence is. So what we're going to do is that we're going to try all possible ways to fill in this missing portion, and then score each and every one. So in the case of the previous example, Barack Obama is the 44th president of the United States, is going to be one of them. We're going to check all possible things. Barack Obama was the first president of the United States. Barack Obama was the second president of the United States. Barack Obama was the first secretary of the United States. Barack Obama was the second secretary of the United States. All possible things. We let language model score all of them, and then we pick the one that is most probable according to our language model. That solves the problem. That's simple. Right? That sounds simple. Now, unfortunately, it turned out autoregressive model is a pretty horrible way to do so because of the inefficiency. We really literally have to try all possible missing portions in order to choose the best one. Now, if we were working in this nice world where we are working with the sequence of the continuous variables, and if we knew the length of the sequence in advance, in that kind of nice scenario, which is actually where the image inpainting happens, there, we don't actually need to try all possible things. We're going to use the tool that we have been talking about over and over. We can use the gradient descent, or the gradient ascent in this case, because we'll be able to compute the gradient of this low probability of this full sequence with respect to the y, the missing variables. And then that only works if the y is continuous variable. Unfortunately, we are in the place where, first of all, we often don't know the final length of the sequence, the best length of the sequence. And even if we do, the y, or the x pre x post y is going to be a very high dimensional discrete values. And then with the discrete variables, what do we not have? We don't have the gradient, right? So this is extremely important point, but somehow people just ignore often is that if the input is discrete, you cannot compute the Jacobian of the output of this neural network with respect to the input is not defined. You can't really do that. Now, of course, you might say, yeah, we'll just relax here, saying that it's just the points in the suffix, so simplex. So why can't we just do the gradient? You can, but it's not going to have any meaning because you have to moving a little in this simplex doesn't really correspond to moving from one point in this one space to another point. Because what was the reason why we used the one space, one vectors? Because there's no similarity between all those things. Everything is equidistant away from each other. So we can't really do that. And then what that means is that the computational complexity of solving this problem with the autoregressive language model grows exponentially with respect to the length of this y. So we're going to just assume that we know the length of y to make the problem so much easier. But even then, the complexity grows really, really fast. And then we don't want, so it doesn't look like a good idea. But then what you notice is that by looking at this one, you notice that we can rewrite this as argmax over y of the log p of y given x pre x post plus log p of x pre and x post. So these two are equivalent just because this is the definition of the conditional probabilities, right? So we have the x is the missing thing, and then we are looking at the probability distribution over this missing bits given the observed bits, and then we have the prior distribution over this observed bits. Interesting thing, this second term does not depend on y. We don't really care y changes, the second thing is same, so we can just safely ignore this because it's constant with respect to y. Now what this means is that if we had a conditional distribution over this missing bits given the observed points, then all we need to do is we can actually solve this second problem rather than the first problem. And what is the second part? Second part, this log p of y given x pre and x post can be thought of as masking out some intermediate words in a given text and then asking a neural net to reconstruct them. So what do I mean by that? Let's say we have a sequence, x1, x2, all the way to x, let's say small t minus 1, and then there's y, and then x t plus size of y. I have to be careful now. So let's say t, because y can be multiple words long, all the way to x capital T. And then this is the thing that is missing. and then the others are the ones that are being observed, that have been already observed. And then in some sense, given this, what we're going to do is x2, xt, mask, there will be as many masks as there are the length of the y, xt plus length of y all the way to xt. So we're trying to mapping this input into one. So what it's saying is that because this is essentially text classification, right? If y, the length of the y is 1, this is like text classification, but even if the length of the y is really long, it doesn't really matter. We're going to think about all possible value of y and then consider each and every one of them as the category or the class in the classification. And what is this? This is just text classification. So again, going back to the second week or the first week, classification turned out to be one of the most important ingredients of modern natural language processing. And then what that means is that we just need to make a neural net that's going to take as the input this variable length sequence where some parts are masked out. And then given this masked out or the corrupted sequence, this neural net's job is to reconstruct or to predict what the missing tokens are. And if you can do that, instead of solving this very expensive problem where we need to try all possible y, and then fit the all possible sequences into the autoregressive model and then get the score and then pick the one best, here we're going to just do the classification. Then we know how to infer or do the inference on the classification so much better. So what this means is that it is still the problem of language modeling, but what this tells us is that there are many different ways to do language modeling. And then one way to think about how to do language modeling is to think about solving this problem of in-painting. Let's see, what's the time? 6:30. Okay, we just continue. We're going to just push all the way until we run out of time, because I already sense that we're running out of time. So let's just make it a bit more general. So I'm going to use the indices of the masked out tokens, right? The indices of the masked out tokens are going to be M1, M2, and Tm. So there will be capital T and many words that are going to be masked out. And then these M1, M2, and then MTM refer to those indices. And then we need to have the observed indices. And here, I think we're going to use O1, O2, and OTO, where TM plus TO is at T. And then we're going to say that these are mutually exclusive. So we're essentially partitioning the input sequence into two sets of tokens that have no overlap. And then one set is going to the tokens, whereas they're going to be masked out. And then the other are going to be the ones that are going to be left in. Then the idea is to introduce a corruption function that replaces each and every words that corresponds to the masked out index with the token mask. And what we want to do, so we do the partitioning, we corrupt the sequence, and then the third thing we do with the neural net is to compute P of xm1, xm2, all the way to xm, tm, given corrupt x. So we are asking, we want to compute this distribution over those missing tokens, given the input sequence that has everything except for those missing tokens. So we're trying to look at what is the context in which these missing tokens can be reconstructed. As you can see, one issue is that if Tm is large, this is a very difficult text classification problem because number of the classes grows with respect to the Tm, right? Number of masked out tokens. So for efficiency, for the purpose of efficiency, we're going to assume the mutual independence among all those masked out tokens, meaning that we are going to rewrite it as a product of reconstructing one missing token at a time. Without not at a time, each missing token all in parallel without taking into account what other missing values are going to be. Now this is a pretty crude approximation, right? Why is that so?
Because they probably aren't actually independent, which ones are passed out.
Okay, I like the answer, yes. So we made an independence assumption, so it's very bad idea because they're probably not independent, yes. So I was thinking more about, okay, what would be example of such case? What would be the example of such a dependencies? Yes.
Like you had a sentence where all the words didn't relate to each other.
Sorry, can you speak up a bit?
Like if you had a sentence where all the words did not relate to each other.
If the words are not related to each other, I guess that's fine. I was thinking more about a much simpler example. Is that let's say the sentence is about here are the let's say blah and blah 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 and blah are the countries where Portuguese is used as the official language. Now I need to guess these three words, right? Now the thing is, let's assume that there are three countries, indeed only three countries in the world that speak Portuguese as official language. I guess Portugal, Brazil. Let's say only two.
Mozambique.
Mozambique, okay, Mozambique, okay. So we have three countries, let's say. I'm pretty sure there must be more, but let's say it is three. Now, I cannot actually predict whether I should put Portuguese in the first position or not without knowing whether Portuguese showed up in the second or third position. I cannot tell whether I should put Brazil in the second position or not unless I know that the first position was taken by Portugal or Mozambique, and third one also was taken by either Portugal or Mozambique. Same thing with the Mozambique. I can't put Mozambique on the third one unless I know that I already have said Brazil and Portugal. So this one is ignoring that one, right? So that's the reason why this is a crude approximation. But then let's just say that for now we're going to stick to this for the issue for computational complexity issue, and then we're going to get to why this is not that big of an issue eventually. Now this is really nice with this kind of assumption. Now you together with using this self-attention, everything can be computed in parallel, all the way to computing the low probability of the correct token at that position for all those positions. Everything can be computed largely in parallel. And then there is a reason why this way of building a masked language model, it goes together really, really well with the so-called transformers that we just learned about earlier today and the self-attention algorithm. Now so this is the one kind of one step of doing the masked language modeling or the in-training or the trying to predict the conditional distribution. Now, how are we going to train this model? At this point, I don't even have to tell you, right? What should be the loss function? It's going to be the sum of the negative low probability of the correct token at the masked out position given this corrupted input. And then now where do we get the corruption function? We're going to simply make the corruption to be as low as possible. So we're going to try all possible ways in which we can select which tokens to mask out and which other tokens to mask in. And that decision is going to be stochastic. Every time we take a mini batch and then trying to compute this stochastic gradient on this mini batch for each example, we're going to toss a coin in a way that however you want for each of the locations to decide whether you're going to put that we're going to mask out that particular word or not. And then that's going to give you this corrupt of the input for each of the examples in the mini batch. And then you know what are masked out versions, so you can now compute the low probability of the correct, let's say, masked out word, and then you just sum them all. or actually sum them across, sum within the sequence, single sequence, and then average across the sequences in the middle. And then you just train this model nonstop. Now the amount of the training examples you have is pretty much infinite, right? So every time you draw a new partition, there's a new example. So if I just write down the subjective function here, J of theta, so I'm saying objective function because I'm going to just write it as something that we maximize. It's going to be 1 over n, and it's the number of the examples, n over n. And now here comes the expectation. So where we're going to sample from this underlying distribution of corruption. So that one gives us a random partition of the mid masked out and then observed tokens given the length of the example, that is Tn. And within this expectation, we look at the sum of the log probability of the correct word that was masked out given all the observed ones. And then we get the observed ones by simply replacing the masked out ones with the masked out one with the special token that is masked. Because we can't really compute this expectation exactly, we use the Monte Carlo approximation, that is we draw the sample, couple of samples, and then compute this approximate this expectation and thereby approximate the gradient descent. And once we train a model like this, so if we use a self-attention on the transformer as a parameterization, we use the subjective function or the negative loss function here that is trying to predict the missing or the masked out token. What you end up with is what people call BERT. That's how you end up with BERT. So you train a transformer with this particular objective function, then you end up with BERT that a lot of people use. Yes.
Sorry, is the squiggly T,
Right.
is that a transformer?
So squiggly T is the distribution over the partition. So we always partition into the observed and the unobserved portion given the length. And then that, so you can think of T as a distribution over that. But distribution can be a bit arbitrary as long as it covers many different scenarios. So we compute the expectation over that one, and then we maximize this objective function with the transformers. That's how we end up with BERT. Okay. All good with the mask language model and the imitating part and so on. Take one person.
This data are input into the gradient, into the stochastic batch gradient.
Sorry, can you actually speak up again? Sorry, okay. Not speak up. I'm sorry. Repeat. I'm lowering it. Okay.
Sorry, I was just asking about what theta is inside of the objective function.
Oh, the data. Yes. Oops. Yeah, you're right. So I forgot to actually put the superscript here. So we have the capital and many data, and then each of the data point is a sequence of length Tn, and then based on the sample we draw from this squiggly T of the Tn, we are going to try to predict the correct, let's say, missing parts given the observed one. Okay. Okay, all right. Now, this is BERT, and then there are many different variants. There's BERT, there's BERTA, there's learning. All these, the natural language processing people went completely nuts and crazy about these Muppet shows. So I don't know why they are naming like that. I can't really remember what those names are. But anyway, so there's a lot of variants. But at the end of the day, the idea is all same. So we're going to try to learn these conditional distributions rather than the training an auto-regressive language model. But then there comes and then all these things are collectively called. I don't really like this terminology, but this is what everyone says. So mask language models. And mask because we use mask, like literally as a mask. So we mask some of the missing value, missing words, and then trying to predict that one. That's why we call it often masked language model. But then, of course, we have to think about why it's called language model. If we go all the way back to the beginning of in the third week or the third week, we talked quite extensively about what language model is. Now, what was the language model? The definition of the language model that we kind of converged toward was a language model gives us a score of a given sequence. The given text, now how probable the text is. So we need to get a scale about it. But looking at this, how we train this masked language model, where we started from this independent objective, right? This independent objective. Can we actually compute a score of an entire any given sequence with this masked language model? That's the question we need to ask, right? Then if the answer is yes, then we can safely call this a masked language model. If the answer is no, then we have to rethink the whole idea of why we are calling it language model. It turned out that there are at least 3 different ways to define a language model using masked language model, which is pretty horrible because the people starting from the bottom and then trying to compare it to the language model. So there are many different ways, but I'll just quickly go through all 3 of them in 2 minutes. So one, now if we actually did ensure that this stochastic process or the distribution over the partitioning was indeed uniform over everything, and now our model was so powerful that it has actually learned all possible conditionals, then what that means is that it has actually learned how to be autoregressive as well. So what we're going to do is we're going to, once training is done, we say P of X should be the product of the conditionals going from t equals 1 to large T, where it's going to be P of X T given X1 all the way to X T minus 1. And then from here, xt plus 1 is going to be masked out. And then all the way to xt masked out. So these are the observed ones, and then these are the masked ones. And then this one is also masked one. Right? And then if you think about it, you can imagine that if we use really all possible partitioning during training, this must have been there as well, where everything up to time step t minus 1 were masked in, and everything from time step t all the way to the end were masked out. And then if that kind of partition was there, then we did actually train a model to try to predict the xt given all the observed tokens up to t minus 1. So then perhaps if the training can be done really perfectly, then simply writing this in this way makes sense. Turned out that in practice that's not the case, but this is one way to put this into a language model. And then because we can now compute the actual log probability of any given sequence, we may be confident in calling it a language model. Now, second way, so there are some challenges, but we don't really have time. So the second way is to define a so-called energy-based model. And then the energy-based model has become like a super popular term thanks to Jan. So I'm not going to go into detail, but I'm going to ask you to take the different course. We're going to define so-called the score. So that's going to be like the negative energy as the so-called pseudo likelihood. That is, we're going to go through T1 to T, where we look at the probability of predicting that work when given all the other words in the sequence except for that particular one. And then we just sum them up, and then this is what we call log pseudo likelihood, or the pseudo log likelihood. Yeah, pseudo log likelihood. Okay. This is not the correct log probability because we are actually looking at the future words, right? It's not a correct log probability, so they don't really sum to 1, when we exponentiate and so on. However, what we can do is we can use this as the so-called negative energy. And then using from the negative energy, we can turn it into the probability by, what do we do? Softmax. Where X prime is in the set of the language. So L is going to be our language set. It contains all possible sequence text here. So if we start from f of x, which is the negative energy, which is the pseudo log likelihood, we can turn it into the actual probability distribution by normalizing, exponentiating first, so making everything non-negative, and then normalizing them by dividing by the sum of those exponentiated values. This is great, except that there's absolutely no way we can compute this normalization constant. This is a summation over all possible text. And that if we could compute that quantity, the NLP and natural language generation is solved, like literally solved. Unfortunately, we can't compute that one. So that's an issue. So this second approach is often called as an energy-based language model or the globally normalized United language model, but the terminologies are not really important, but it is the fact is that we can use this masked language model to generate a score for each of the sentences, and then we can turn those scores into probabilities by using softmax, which is often computationally intractable. The last way is the implicit way. And due to the timing, we're going to talk about this next week. All right, that's dismissed.